our last section in chapter 1, section 7. This is a shorter section, which is great because section 5 and section 6 were definitely not short sections. Looking at complex numbers. This is building off of what we've already talked about in regards to exponents, in regard to squares specifically. So square roots, we've already talked about this already. We had a lesson or a couple lessons that have involved square roots. So if we have x squared equals 25, we can figure out what the solution for this would be. X could be 5 squared is 25, or x could be negative 5. Negative 5 times negative 5 is 25. So we get two different solutions, two possible answers, and that we can do that. The issue we ran into is something like this. X squared equals negative 25. This caused a problem because 5 times 5 is positive 25. Negative 5 times negative 5 is a positive 25. We couldn't come up with a real number that worked here. Something times itself equals negative 25. There is no real number that can do that. And this is where we delve into our complex numbers, our new ideas. We have to be able to deal with this when it happens, and we need a new system for that. So we need to define the number I, which is odd that we have the number I. My daughter looked at me very funny and said, I is a letter. And I did not go into it with her as to why we were learning about the number I. But I represents the square root of negative 1, which again does not exist as a real number, but we're going to define it as an imaginary number. So this imaginary number I is the square root of negative 1, which of course means that I squared, square root of negative 1 times square root of negative 1 gives us negative 1. So let's see how this works. If we were trying to solve this, we're trying to figure out or evaluate this. The square root of negative 25. What is the square root of negative 25? By using this new number I, by using this new concept of an imaginary number, we can split negative 25 up. We can separate that out into two factors, negative 1 and 25. Negative 1 times 25 is negative 25. The reason for that, or the point of doing that, is we cannot deal with the square root of negative 25 as it is. However, by defining I to be the square root of negative 1, and now we have this negative 1 here, we can separate the square root. We can separate the square root of negative 25 into the square root of negative 1 and the square root of 25. We're back to, I forget which section, an earlier section, maybe section 4, 2, or something like that. We had a property of radicals that said the square root of x times the square root of y gives us the square root of x times y, so we can put them underneath the same square root, and we can separate them. So we do have a property that allows us to do this. Now that we have that, the square root of negative 1 we have defined to be I, and the square root of 25 we know is 5. So the square root of negative 25 gives us I times 5. And that square root of 25, by separating out the square root of negative 1, we could deal with the 25. We could deal with this number as a positive and leave this negative 1 out as I. Now, this is correct. I times 5 is correct. However, it's proper notation to put the numeral first. Even though I is not a variable, so 5, we couldn't call it a coefficient. It's just proper notation. We put the number first. If you put I times 5, it's technically correct, but proper notation says we put the number first. All right, let's look at a couple more examples. Once we have that imaginary piece, then we can create these complex numbers. And so a complex number is a real part, a real number. A is a real number, and B is an imaginary number. And so a complex number is a combination of real parts and complex parts. It's a real number plus an imaginary number. And I'm going to let you read through that if you want. I'm going to give you kind of a visual. Throughout history, mathematicians and people in general are very visual learners. Even if you don't think you're a visual learner, we have a hard time accepting things that we can't perceive visually. And so imaginary numbers have been around for a very, 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 very long time, hundreds of years. At one point, they call them ghost numbers. They kind of appeared in these problems, and then they worked themselves out. And so it wasn't a big issue, but they were there. And eventually, a guy named, I think it was Euler, was able to graph them and kind of visually show what they look like. And at that point, mathematicians started to accept them more. And now we accept them fully. So here's a visual interpretation of what's going on. We've got two axes here, not our x and y axis. So it's not our typical xy axis. This is the real number line. So all the numbers that you know and love, 1, 2, 3, 1.5 is in there, 2.5 is in there, 2 3/4 is in there, pi, 3.1415, blah, 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 pi is in there. All the irrational numbers, square root of 2 is somewhere around here somewhere.